Hello everyone and welcome to Texas Tech University's Project Lab 1 tutorial videos. I'm one of the tutors for this course. My name is Daniel, and in this video I'm going to show you how to get started with Vivado and the Basis 3 board. Alright, so first we are going to go to Google and get familiar with the Basis 3 board. So Google Basis 3, click on this link, and it'll bring you to this Digilent website. Gives you a lot of information that you can use for your budget, and just in your presentation in general to show that you know how your board operates and what kind of components are available on it. So it shows a few pictures, describes the board here a little bit, tells you that it uses the Arctic 7 FPGA, that it does not come with the USB cable, some input and output information, talks about the clock, talks about the connectors, so you have a USB A, regular one, the USB micro B, 4 12-pin PMOD ports, and a VGA port. Talks about the RAM, a lot of more features here, how many switches, how many LEDs, how many push buttons, how many 7 segments. And then here are some good videos to start off with. You can skip the unboxing one, but Basis 3 introduction here is really good in-depth analysis of the entire board. It even looks at some schematics and stuff, or how the board works internally. This getting started with Basis 3 in Vivado is also a good video. This is how I started with learning Vivado and the Basis 3 board, and I still reference it, so it's a great place to get started and look these over before you even start playing or programming with your Basis 3 board. So the next thing you want to do is come to this data sheet, open up the data sheet, and then look this over also. This is good information on the flip-flops, amount of registers you have, memory. Good information is how to access your PMOD ports and what the location is, so you can assign them on your code, on your Xilinx verilog code. Here you can also see that it identifies each component on the board for you. So it tells you which ones are the PMOD ports, which ones are the 7 segments, LED switches, everything that's available here on your board. Then it talks about power supply, that you do need a 5 volts external power supply. Here in this diagram you can see that you can be either powered by this 5 volt external power supply or your micro USB port. So either one of those can power the board, but it does need this selector, which is a little blue jumper that you can select to either 5 volt external or use the USB power. We'll go over that later in the part where we actually program the Basis 3 board, but this is good information to look over, so that way when I start talking about it, you know what it means, you know what I'm talking about. Again, here's more information on the power supply of the in and out ports, the PMOD ports, and typical and current, max current. Talks about the Arctic 7, how it can be programmed through 3 different modes: the SPI, the JTAG, or the USB mode. And it goes in depth about the 3 different programming modes. We will be using the SPI. I'll be showing you how to use the SPI mode, which is the only way where you can actually store a program onto internal memory called SPI flash. And so that way you can turn off your board and turn it back on, and the program will still be on there however many times you turn off and on and off your board. So I'll show you that when it comes to hardware programming. Now just continue looking over the data sheet, look over the oscillator because this is important. You gotta know what your clock runs at. So here it says 100 megahertz. You gotta figure out how much time one of those ticks on that 100 megahertz clock actually represents. And we'll get to that once we start counting ticks and doing stuff with frequency counters and servos and motors and plenty of other things. So again, most of this far into the data sheet might be beyond your scope. You might understand some of this, but it's good just to look it over and get familiar with it, so that in the future it might make sense. But even this VGA port section, if you ever end up needing to use your VGA port, here's a good place to come find the pin out and the location of each one of these pins. So most of the rest of this, except for this 7 segment, the rest of this data sheet might be beyond your scope. But again, it's good to look at. Again, all of these little diagrams are helpful. As you see, this one tells you which pin is which on this PMOD. So looking at it, on the top you have G2, on the bottom you have G3, and so forth and so on. And on this side, powers are on the bottom. This side, powers are on the top. So get familiar with this data sheet, so that way we have no issues with the board whenever you start programming more sophisticated modules and programs. Alright, so now to get started, I will open up my Vivado software. Create a new project, and it's going to open up this wizard that you just want to go through. This project, I'm going to call it tutorial 1_1. It's going to be an RTL project. Won't specify sources at this time. In future videos I will show you what that means and how to use it. But for now, just click on that. Here we're going to have to select the FPGA type we are using. So we are using the Arctic 7. Package is CPG 236. CPG 236. Speed grade should be -1. And from the last 3, you just want to select the 7XC7835. So again, this is important because it assigns all the inputs and outputs to the chip that you're working on. If you end up working on a different board or chip, you will select the appropriate family, package, and speed grade. Okay, hit next and hit finish. Just create the project. I know it seems like a lot right now, but if you just write some of these key things down, it'll sink in after doing it so much, and you won't have any issue. So it'll pop up this summary and manager for you, the project manager up here, project summary, and the design runs down here. So first, scoot that down, scoot this over, and in here in our project sources, I'm going to hit add sources. Here we're going to create our new module, so it's going to be add create design source, and next. If you had some files or some code that you had written before that you wanted to add, you could just go to add file and select it here. But we will be creating a file. It's going to be a verilog file type. We're going to call it switches. switches 4. Okay, and then we're gonna highlight it, hit finish, and it'll pop up this wizard to help you select your inputs and outputs. So we're gonna be having 4 switches. So SW0, it's gonna be an input. SW1 is also going to be an input. SW2 and SW3. So those are our 4 inputs. Now we can assign outputs. We're going to go to 4 LEDs. So LED 0 will be an output. LED 1, another output. And continue with our outputs. So there we go. We have assigned all of our inputs and outputs for this module. I know there's this additional option called in and out. For the simplicity of these modules, I would recommend sticking with input and output, and you can learn in and out on a different course or future use of the software. So for now, all your inputs, SWs, are outputs, LEDs. Hit OK, and it'll create the module for you. Here it's called switches 4, and it created it and added it to the design source and to the simulation source. So we can double click on it to open it up. Here is the typical header that it creates for you. You can delete it or fill it in if you want. And then we come to the actual module itself. This is the entire module for now. All it does is set up this inputs and outputs for you here, since we don't specify the number of bits we want. It defaults to giving each one of these 1 bit. So SW0 is 1 bit, SW1 1 bit, 2, 3 is 1 bit, and LED 1 through 3, 0 through 3 are also 1 bit. You notice here we do not have a comma on the last entry. That is standard for verilog input-output headers. So that is correct, and that is the correct way for a header to be. So now to make a simple module so that we can show you how to make a module and simulate it and program it, I will just assign the switches to the LEDs. So to assign something is assign, and then it's the output, so LED 0 equals the input, W0, semicolon. So highlight this, copy it, and do it for each one of the LEDs, so that if any of these switches change, the appropriate LED will change also. So again, this is a really simple module. The purpose of this video is to show you how to create a module, simulate it, and program it all simultaneously so that you can have the best performance of your module. So this module is complete. We're going to go ahead and save it. It'll check for syntax. Everything's good. If they would have had any syntax error, it would have told you here in the sources window. So the next thing to do is simulate it. So we'll come up here to our sources window. We will hit new source. Actually, as soon as you finish your module, which we did, we save it, and then you run synthesis. So highlight it and run synthesis. And it should take a few seconds, but it should be good to go. Don't see any errors. It's not much code here, so not much room to make errors. So again, once this finish synthesizes, which it just did, complete, successful, we can close this and we can create our test bench. So to create a test bench, you go to sources, then add sources. You're going to create a simulation source. Next, and again we're going to create a file, and we're going to go with the conventional switches for underscore test bench. So this is typical standard way I do it, so that way I know that this test bench that I just created goes with that switches module that I created, and that this is only a test bench because you can't program test benches to any hardware. Okay, so now I hit OK. You can highlight it, hit finish, and it'll want you to assign label your inputs and outputs. But for test benches, we don't need inputs and outputs. Yes, and there it goes. It created this module called test benches, switches underscore test benches. One thing you will see sometimes is that whenever it makes it, it sometimes adds it to the switches, to the design sources folder and the constraints folder. Any test bench, you only want it to exist in the simulation folder because it's only used for simulation. So to fix that, you will highlight the test bench. You would go to this box right underneath it. And this is all the properties of that source file. As you see, it says switches for underscore test bench. Scroll down. You see where it's used in. It's checked all places it's been used in. So we only want this test bench to exist in simulation. So we're going to go ahead and unclick synthesis and unclick implementation. So again, we only want this test bench to exist in simulation. So that's why we highlighted it up here and came down to the properties and made sure that that is the only option selected. Alright, so to verify that, we come up here and we see that test benches only exists under simulation. It does not exist in constraints or in design sources. Alright, so now that we are sure the test bench is in the appropriate place, we can open it up and start writing your test bench. So if you look at this fancy test bench, you'll see that it looks just like your module that we just made, the switches module we made, except it doesn't have any inputs and outputs because we didn't assign any. So what we want to do in this test bench, every time I create a test bench, I go through 3 steps. Step 1 is to copy all the inputs and outputs from the module I am test benching, and I paste them, but instead of leaving them as inputs and outputs, I make all the inputs registers. Do that real quick. And all the outputs will be wires. So that is step 1. Make all your inputs into registers and all your outputs into wires. But notice we are doing this outside of the parentheses and semicolon that go with a name. In your regular module, your inputs and outputs go inside the semicolon that go with a name. In your test bench, your registers and wires go outside of the semicolon, in the parentheses and semicolon, and they're all followed by a semicolon. So what we're doing here is creating registers that we will change the status of them We can assign them to be zeros or ones, as if we were switching the physical switches on the basis board. So step 1 is to make your inputs registers, output LED, output wires. Step 2 is to instantiate your module that you want to test bench. So instantiation is a way of controlling another module within this module. So it's actually way more complicated than that, but that is the most simplest way I can explain it without confusing everybody. So instantiation, I'm not sure if that's spelled right, but all we want to do is put the name of the module that we want to instantiate. So it's called switches. Make sure it's correctly spelled. SWITCHES 4, and we will call this the unit under test. And then we open parentheses, and we list the inputs, which is W0, W1, 2, 3. So the order it goes in is inputs followed by outputs. So I listed all my inputs, now all the outputs. Some commas there. And so that's the instantiation line. This is the name of the module again that we want to instantiate. It's called unit under test, UUT, and all your inputs and outputs. So if I hit save, it'll check your syntax, and if it's correctly done, you should see that switches 4 is now listed underneath the test bench as the unit under test, which is correctly instantiated. If it wasn't correctly instantiated, there'd be two separate entries as it was right before I saved. Okay, so it's correctly instantiated. So the next thing we have to do is perform some stimulus. So to do that, caps off, and it should begin. Spelled it right. Did not. So initial begin, and now you just have to make the registers what you want them to be. So first I will 0, then all out. 0. 2, 0, 3, 0. So now they're all 0. I will add a delay. This hashtag 100, it only works for test benches, but it's a way to add a delay. It actually adds 100 ticks. It waits 100 ticks before it moves on to the next line. So again, it only works for test benches, but it's a great way to add delay in between your changes. So to change stuff, I'm going to copy all these. And paste them. However, I'll make sure I change some switches around to see what happens to the LEDs. I mean, I'm sure we all know what will happen, but in the event you didn't know, this would be how you would test. And we are testing the module to make sure that it's doing what it's supposed to. Alright, so So set this one to 0 and this one 1. This one 0 and this one 1. Now we can test the third one, right? And for the last test, I will make them all 1. And then reset them back to 0. Alright, so what we're doing here is telling it to initialize all of them at 0, wait 100 nanoseconds, or 100 ticks, then change switch 1 to 1, and all the rest of them to 0, wait another 100, switch 1 to 1, the rest of them to 0, switch 2 to 1, rest of them to 0, and so forth, so on, just so we can test each switch, make sure it turns on the LED, and then see what happens when they're all turned on, and then reset them back to 0. So all it misses is a end for the begin. So this begin needs an end to go with it, so that would be this one, and then an end module. So if we save this, it should be good to go. No syntax errors. Alright, so this looks good. I can fix this backspace issue if it frustrates anybody else. Not OCD, but maybe I am. Maybe some of you are. Anyway, it's just more visually appealing and easier to see what's happening. Of course, all those spaces had no actual effect on the code, so you could have left them in there if you wanted to. Anyway, so we resave that, and test bench is complete. So I highlight it again, and to simulate it, we just run simulation. So now again, now that this test bench is complete, so first we made sure that all the inputs registered, all the outputs for wires, instantiated the module we wanted, assigned the inputs and outputs, and now we're changing the inputs to see what happens to the outputs. Alright, so to do that, you highlight it and you run simulation on here on the left. Run behavioral simulation. Just take a second, and there we go. So here it shows you all the objects, all the inputs and the outputs. It tells you their values, their data type. And here is the whole simulation. So if you click on the zoom to fit, we can see what happened. So as our code said, for the first 100 nanoseconds, 100 ticks, they're all 0. And the second 100 ticks, we hit switch 0 to be 1, and it turned LED 0 to be 1. 100 nanoseconds later, or 100 ticks later, switch 1 goes to 1, and LED 1 goes to 1, and again switch 2 goes to 1, LED 2 goes to 1, and then for the last case, switch 3 goes to 1, LED 3 turns on, and then they all go to 1, and again they all go to 0. So our simulation shows that everything is happening the way it's supposed to. You can see how each individual signal changes and how it affects the outputs. So the biggest incentive of test benching all your modules is that you can see what the status of each signal is at each nanosecond precisely. For this specific module, it might be kind of unnecessary to make a test bench, but it's a good way to prove that your module works, and it's a good way to debug. So say one of your signals wasn't working properly. Say SW1 wasn't turning LED 1 the way it's supposed to. Here in simulation, you can visually see the status of each element, so that way you can identify the issue. Once you program your code onto the Basis 3 board, you can't see what each signal is doing. So debugging on the board itself is a lot more difficult than debugging here in the simulation and seeing what each signal is doing, opposed to not seeing what the signals are doing on the hardware. So again, test benches are awesome for debugging and for proving that your module, your code works exactly as planned. Alright, so this is complete. We can close this out. Close simulation. Okay. Close that test bench. You're done with test benching. You can move back to switches 4, design source. And the next thing to do is to program our Basis 3 board with the code we just made. So to do that, first we have to add constraints. Constraints is how we associate all of our inputs, our labels here. So we know we have 4 inputs. One's called SW0, SW1, SW2, and SW3. But we have to assign them to an actual position on your Basis board. So whenever we were looking at the data sheet, as you saw that each position, each port, each LED has a label that goes with it. So this one would be L17. The switches and the LEDs also have a label that goes with them. So to create so to assign these registers, these inputs and outputs that we made to their appropriate switches on the hardware, that's where we have to create this constraint. So to do that, we highlight constraint and hit add source, and we're going to do add create constraints. Hit next and create file. It's going to be XTC file name. I'll call it switches underscore XTC. And then highlight it, hit finish. And then you should see it pop up under constraints here. So switches XTC, it should only be in that location, not in switches XTC does not exist in design source or in simulation. It only exists in constraints. So we can double click on that. You'll see that this is just a blank page. So to set up your XTC, we go to Google again. We Google Basis 3 Master XTC. The first few links, it takes you back to the Digilent site. You can find it there. And there's a lot more resources in the Digilent site than I covered, so it's a good place to go and look around there. But if you go to this third one that says GitHub, it actually pops it up without you having to search. So all you have to do is copy this entire 294 lines of code. Copy it and paste it in the XTC file. So as you see, all of these hashtags in the XTC are the comments. and most of the stuff is commented out. But if we look through it, you can see that if you wanted to use the SPI flash, this is how to set that up. The USB, RS-232, VGA connectors. Here is keymod headers. Since they're purple, I'm going to go ahead and comment them out real quick because I don't need them. Comment. So that they're all gray. So make sure everything's gray commented out. So all these PMOD ports, you can see what their location is and their label, all the buttons there. Here looks like the 7 segment. Let's scroll down again. Comment that out. I'm not using 7 segment. And LEDs, here we go. So we will need some LEDs for now. Let's see. I will comment all those out. So notice it says the pin location, and this would be the label, the name. So pin U16, if you actually look at your basis board, let's see, U16. On our XTC that we just copied, you see that says package pin U16, and that corresponds to this LED on the far right here, U16. So in this bracket is where you put your label, your input. So ours is LED 0. Okay, we're going to delete the brackets because we don't have brackets on our actual name. So this is what I'm referring to. So LED 0 is all one word. So it needs to be exactly like that. All LED 0, no brackets. Same thing. LED 1, no brackets. So there's all of our LEDs. Now right above here you see all the switches. I will uncomment these. And again, our switches are capital SW0. So delete this. Capital SW0, 0, 1, 2, Alright, so I assign all my switches to their location. SW0 goes there, SW1 goes there, SW3, good to go. Clock, we're not using the clock right now, so I'll go ahead and comment that out. So we have our switches that we need and our LEDs that we need. Everything else has been commented out. And we're good to go. So we can go ahead and save this. Now we can come back to switches. And go ahead and rerun synthesis. Alright, so it's running the synthesis here. And once the synthesis is complete, the last thing we have to do is set up the settings for the SPI so we can program the code we just made onto the SPI of the Basis 3 board. Let's go ahead and close this out. To set that up, all we have to do is highlight switches, go to tools, project settings, and we'll go to bitstream and select bin file. Bin file is what we need to load that file onto the SPI so that it can stay on the board longer. So I hit apply and then OK. And again, let me rerun synthesis real quick. Run, yes. But this time, as soon as the synthesize completes, we're going to go ahead and open synthesize design. So once that window pops up, so there we go, complete, open synthesize design, okay. Alright, so that's done. We go to tools, project settings, edit, device properties. And in general, we want to make sure that this first one is true. And then we go to configuration, make sure that the rate is that the rate is 33. Then you go to configuration mode and you select the SPI times 4. Just hit the little box right here. And that's it, hit OK. Then we can go ahead and close the synthesize design here. Make sure you save it. And now we're going to have a bunch of more options under synthesize, but what we want to do next is generate bit stream. Yes. Here under the log, you can actually see what's happening. It'll tell you the progress, status, and everything. How many errors, how long it takes for your program to run. What I'm looking for is the .bin file complete. Still running. And finally up here it says right bit stream complete. So now we open the hardware manager and we turn on our basis board. So once you have opened your hardware manager and we have created our bit file and our bin file, now it is time to program the hardware device. So this again is step 3 of how to create a successful module. Step 1 would be write the module, synthesize it. Step 2 would be simulate it using the simulation that we did. And then step 3 would be finally to program your device and test it on the hardware. So Vivado has this hardware manager that makes it easy to program your device. All you have to do is open the target. Before we open the target, you want to make sure you plug in your basis board via USB to your computer and make sure you turn it on. Just a quick show you my basis board here. It's being programmed by the USB up top, but it's being powered by the 5-volt regulator that goes to this 2-pin input here. In order to do that, you do have to switch this little jumper or blue jumper to the external position. So there's 3 pins. Put the jumper on the 2 pins that say EXT, so that way you can power it through the external port and not through the USB. Alright, so mine's turned on. You see the little power LED on at the very top. It's plugged into my computer. So now I can open target, open new target, you open up this wizard, hit next, local server, hit next, and it'll search for the device, and there we go, it found it. The clock frequency though does have to be changed. You want to select 30 megahertz and then select your hardware here and hit next. And then it gives you a summary, so hit finish, and then it connects to your device. So let's scroll down, remove this for just a second. So as I mentioned earlier, there's 2 ways to program the Basis 3 board here, and one way is to program the FPGA directly, and the other way is to program the memory called the SPI, so that way the program that you load onto the board stays on the memory every time you turn it off and on and back off. So if you wanted to program the FPGA directly, you would just highlight, this is the FPGA, the XC7, the Arctic 7 chip. So if you wanted to program the chip directly, you would just right click on this and select program device, and then you would just open this and select the bit file that we just created. So here is already loaded, the bit file. But we don't want to do that. We want to add a memory device. So we're going to right click on it and we're going to add configuration memory device. And we're going to search expansion. And then we're going to select this S25FL032P and hit OK. And hit yes, OK. So now we can program the memory. And to program the memory, that's why we created the bin file. Here it's already selected, but if it's not selected, you can hit on those three little dots and it'll open the browser so you can select your bin file. We'll click on it. Notice that it says erase. It has checked erase, program, and verify, so it'll do those 3 steps. And then you can just hit OK. And that will start programming the bin file onto the SPI memory of the board so that we can run the program as many times as you want to and not have to worry about turning it off and on or having it connected to your computer the whole time. So first, as you saw, it erased and then it programmed. So any program that would have been on there would have gotten erased first, and then it loads the new program. So now it's done. Hit OK. And now we can look at the basis board. And should be able to turn it off. Then you have to switch the jumper to SPI mode. So notice that the jumper is on the middle 2 pins here, so I will take it off and put it on the top 2 pins so it's on SPI mode, and I'll turn it back on. It will load the program we just loaded, and now the switches turn on the LEDs as it's supposed to. So just to show you that we are not connected to the computer, I can unplug the USB and show you that the program has been loaded onto the board and that we're not connected via USB. Now we are just being powered by the 5-volt regulator over here, and our program is still on. And again, we can turn it off, turn it back on. The program will always be on there since we programmed it to the SPI memory on the board, and we do have it set to the SPI mode right up here. Okay, well that concludes this part of the video. In the future videos I will show you how to do other things with the Basis 3 board, and we will make more sophisticated modules. So I hope you learned something, and I'll see you in the next videos.